Fuel cells and power systems. Fuel cells are a unique and historic power storage system. The first fuel cells were developed for the Apollo missions. You will notice that while modern spacecraft have solar panels, the Apollo spacecraft did not. Solar panels at that time were not efficient enough to be useful, and the mass would have been prohibitive. The Lunar Excursion Module, or LEM, had regular batteries, as it would only be used for going down to the moon from low lunar orbit and coming back up. It only had to operate for up to 75 hours. This was the longest time spent on the moon and was accomplished by Apollo 17 with Eugene Cernan and Harrison Schmidt. The command module from the same mission spent 6 days in lunar orbit with Ronald Evans in command. The journey there and back took 3 days each way. They launched on December 7, 1942 and landed on December 19. So 12 days of continuous operation for the command module and 3 days on the moon for the Lunar Excursion Module. How did they do this without solar panels or an RTG? NASA solved this power problem by using fuel cells. The fuel cell used hydrogen and oxygen to produce power, and here is how it worked. Usually to produce power, we put gasoline in our cars and it is burned in a piston-based internal combustion engine. The intake system pulls air into the engine to mix with gasoline for combustion. This is how we power our cars. The internal combustion engine is over 100 years old and works very well, but it can only use about 38% of the available energy in the gasoline. This was not efficient enough for Apollo. They had to find a better way to generate and store power. That much wasted fuel would have a lot of mass. The first crude fuel cell had been invented in 1838 by Sir William Grove. It was little more than a curiosity. It used a sulfuric acid solution as an electrolyte with hydrogen and oxygen input lines and wires completing the circuit. So how did this fuel cell work? You apply electricity to separate hydrogen and oxygen, or make them another way. You put the hydrogen and oxygen on separate sides of a membrane or other separator. Electrons will try to get from the hydrogen to the oxygen. They can leave the hydrogen, allowing the charged hydrogen ion to travel through a membrane that only allows charged particles to travel through it. You make these electrons go through a wire to get around the membrane to the oxygen side. Electrons moving through a wire is what we call electricity. Once on the oxygen side, they can combine with the oxygen and water to produce a hydroxyl ion. It can combine with the hydrogen and produce water. This recombination produces a lot of heat unless you use a catalyst to mediate the reaction. Platinum works best, but is very, very expensive. Nickel can also work, but you must make the pressure of your hydrogen and oxygen gas very high, about 40 atmospheres, or let it operate at a much higher temperature. This system will run as long as you put hydrogen and oxygen in, and the membrane separator stays in good shape. The 1838 fuel cell used sulfuric acid as an electrolyte. In 1932, Francis Thomas Bacon improved the fuel cell using an alkaline electrolyte. This was the type of fuel cell chosen by Apollo. It is about 70% efficient in converting chemical energy from the hydrogen and oxygen into electricity. So you can put hydrogen in one side of a fuel cell, oxygen in the other. The hydrogen can only go through the separator if it gives up an electron. This makes the electron go through a wire to get from one side to the other. The moving electron is used as a power source. This worked so well for Apollo that it was continued for the Space Shuttle program. The Apollo command module had 3 of these alkaline fuel cells. You can see what one looks like here. These fuel cells were fed by hydrogen and oxygen tanks. These were pressurized cryogenic tanks that you can see here and here. Hydrogen has a lot of power per kilogram, but is not very dense. It must be compressed to extremely high pressures to get many kilograms into a tank. Oxygen is easier to work with. The only byproduct of hydrogen fuel cells is pure water, which the crew could use for drinking, and electricity, which they used to run their systems. This gave them both power and a water source. These power cells produce power very efficiently, and if you reverse the process and apply electricity to them, they can break down water into hydrogen and oxygen efficiently too, at about 70 to 80% efficiency. One problem is that while the hydrogen and oxygen fed into the system was pressurized in tanks, the hydrogen and oxygen that is produced by a fuel cell when you apply electrical power to it has to be repressurized back into a tank. It takes quite a bit of energy to compress and cool the gases, and some efficiency is lost there. These systems are of interest here on Earth because they can be used to store excess energy until it is needed. They can be combined with renewable energy sources like solar or wind to help maintain continuous power. For the Apollo missions, they needed a source of long-term power generation, and the hydrogen alkaline fuel cell worked great. Let's take a close look at this design in specific and other types of fuel cells in general. The Apollo fuel cells were, again, alkaline fuel cells. Alkaline fuel cells were a curiosity until NASA needed their unique potential and developed the technology into a usable device. There are other options for fuel cells, like the solid oxide fuel cell, which operates at a high temperature and uses nickel catalyst and zirconia ceramic electrolyte. These run at 900 centigrade and can use many types of fuel like methane, methanol, and ethanol, as well as hydrogen. The high temperature makes them a little dangerous for spaceflight. Getting rid of excess heat in space is already a problem. On Mars, however, extra heat is a good thing, and these might be useful there. Proton exchange membrane fuel cells were used by the Gemini program before the Apollo program, so they were the first American fuel cells to be used in space. You can see one here. Gemini missions 1 through 4 used regular batteries, but 5 and on use these advanced proton exchange membrane fuel cells. They can operate at room temperature up to about 90 centigrade. PEMFCs have a good power to weight ratio and work very well for these small capsules. They are also called polymer electrolyte membrane fuel cells, making the acronym correct with 2 readings. They use a platinum catalyst, which accounts for their relatively low temperature of operation. They are prone to carbon dioxide poisoning, however, and must have pure oxygen. Molten carbonate electrolyte fuel cells operate at 650 centigrade and have useful applications. They can also use fuels other than hydrogen. They are more resistant to impurities than other fuel cells and are not poisoned by CO2. They can also operate with metal catalysts cheaper than platinum. You will find that platinum is very expensive, but it is one of the best catalysts known and reduces the operating temperature in several reactions. The waste heat can be recovered from these and used on Earth in a cogeneration mode to increase efficiency up to 80%. These do have a more limited lifetime due to the higher temperature and corrosive electrolyte. They are also massive and are being used for power plant power production. Acid fuel cells can be solid or liquid acid. The first fuel cell ever made was of the acid type using sulfuric acid. The acid now is usually liquid phosphoric acid in a Teflon bonded silicon carbide matrix. Remember that silicon carbide is a diamond-like crystal with exceedingly high strength and durability. These fuel cells have porous carbon electrodes containing a platinum catalyst. They have a lower power efficiency than other types of fuel cells and have quite a bit of mass. They are used for stationary systems or large buses. Now back to AFCs or alkaline fuel cells. Once again, they use a solution of potassium hydroxide as an electrolyte. Potassium hydroxide is a base or alkali material. They can use metals cheaper than platinum for their electrodes. They have a fast rate of operation and high efficiency. They are also susceptible to CO2 poisoning and must have pure oxygen to work. Fuel cells have thousands of applications. This is how spin-offs such as these returned $7 to the U.S. economy for every $1 spent on the Apollo program. The Apollo engineers had to optimize fuel cells for their unique needs. They needed a low-mass system that could provide enough power for a large capsule with 3 astronauts in it. The first alkaline fuel cells used an electrolyte solution of 30% potassium hydroxide, but the Apollo design had to use a concentration of 83% to prevent evaporation. So we have an electrolyte layer operating at 260 centigrade. We have the platinum metal electrodes, a cathode and an anode. We have the hydrogen feed side and the oxygen side with water where hydroxyl ions are produced. These had 4 atmospheres of gas pressure to increase the reaction rate. The fuel cell had a mass of 110 kilograms. Each cell in the Apollo design generated about 1 volt, so the engineers stacked 31 of them per fuel cell to create a 31 volt power system, but used 28 volts of that to have a little leeway. The AC inverters turned the 28 volt DC into 400 Hz AC. They were heated to operating temperature prior to launch and had a heating system to make sure they did not cool too low. They could not be restarted if the temperature dropped too much. Once the power was generated, let's understand power distribution. The command module produced power from hydrogen and oxygen gas using these fuel cells. It's important to know how these power systems distributed the electricity. Let's look at this now. In this diagram, you see the command module power system schematic. Let's go through the important components, starting from left to right. The first system we see is the cryogenic subsystem. This is where the hydrogen and oxygen tanks were managed and are shown here for oxygen and here for hydrogen. There were 2 tanks for each. The hydrogen tank stored 12.7 kilograms of hydrogen at about 17 atmospheres. Remember, hydrogen is the lightest element and difficult to store. It takes a lot of oxygen by mass to react with an equivalent amount of hydrogen. Hydrogen is 1 mole per gram, so there are 12,700 moles per tank. Each oxygen tank stored about 145 kilograms of oxygen at a little more than 60 atmospheres of pressure. 16 grams per mole, so there are about 9,062 moles of oxygen. The astronauts will be breathing some of the oxygen, and it takes 2 hydrogen atoms per oxygen atom to make a molecule of water. This means the total potential power output of the system would be limited by the amount of hydrogen, since there was a surplus of oxygen. There was enough hydrogen to combine with 6,350 moles of oxygen, so that would leave 2,712 moles of extra oxygen. The oxygen is used for breathing, but is also fed through this system of pipes to the fuel cells. You can see that every fuel cell received a flow of oxygen and hydrogen through the cryogenic manifold. Once operating, they could not be shut down and restarted in space. Each cell could operate independently if something happened to the others. The status of the fuel cells was tracked on this display. You can see a clock showing how long the power system has been operating, warning lights in case there was a power problem, and a lamp test switch to make sure the bulb is still good. Nuclear missile silos in the U.S. used almost exactly the same setup. You can see these gauges that reported the tank pressure and residual oxygen and hydrogen volume. At the bottom we see indicators and control switches for heaters for both hydrogen and oxygen, fans for both, and a pressure indicator for the oxygen surge tank. If the pressure fell below 54 atmospheres or got higher than 65 atmospheres, this warning light would go off. The hydrogen limits were below 15 or above 18.4. Each tank contained a heater to warm the cryogenic fluid and raise the temperature. Remember, PV over T equals PV over T. In a system with an unchanging volume, increasing the temperature will increase the pressure. It was a short in one of these heater units that caused the explosion on Apollo 13. You see an auto switch on the control panel here. When this is on, the heaters and fans work automatically to keep the pressure between the limits described. It would turn the heaters on if both tanks dropped too low, and turn them off if one tank got up to maximum pressure. If this auto switch is set to off, power is cut to the heaters and fans. If the heater switches are manually turned on, they must be watched carefully because it will not automatically turn off if the pressure gets too high. That is why one of the astronauts in the movie Apollo 13 was demanding to know what the pressure was when the heater circuit was tested. The fan switch had to also be manually turned on during heater testing to prevent overheating, as convection doesn't work without gravity and hot air stays in one place instead of rising like it would on Earth. Now, if you watch Apollo 13 again, you will understand exactly what the astronauts were looking at when they were evaluating the fuel cells and the significance of them having to shut them down. In all fairness, the short circuit was determined to be the result of a tank being dropped during construction. Some of the wire was exposed. A hot wire in a tank of pure oxygen is called a bomb. The hydrogen oxygen flow to the fuel cells was controlled by shutoff valves, which were controlled by this panel. The fuel cell reactant switches, seen here. By placing these in the up position, the shutoff valves are opened. When placed down, they are closed. These switches had springs to keep them in the center position. Shutting off these switches during flight will shut down the fuel cells. Since the fuel cells cannot be restarted in flight, this would limit power to the battery systems that we will be describing next. To avoid this happening accidentally, a circuit breaker on panel 226 called the FC Reacts was pulled during flight to cut power to the fuel cell reactant switches, making shutting down the fuel cells in flight a two-step process. The shutoff valves were found to be prone to close themselves with vibration exposure, and they were latched in their open positions by turning the FC Reacts valve switches seen here to latch. This was necessary during any time that the rocket engines were operating or during stage and module separations when there might be vibrations. The indicator here was striped for closed and solid gray for open. The hydrogen oxygen would flow past the shutoff valves and pass through a heater to reach a regulator. The regulator optimized the pressure of the reactants. The fuel cell would then produce steam and electricity. The steam was flushed with hydrogen gas into a condenser, where it was cooled by a water glycol mix, then to a separator that removed any excess hydrogen gas, which was recycled back to the fuel cell. The water was then fed to the Environmental Control System, or ECS, to be available to the astronauts. The water glycol coolant was cycled through the hydrogen and oxygen preheaters to give up some heat there and heat those gases, then sent to radiators so the heat could be radiated into space. There is a coolant pump for each fuel cell that is controlled on the panel by this switch labeled fuel cell pumps. To keep from making the fuel cells too cold, the hydrogen gas at about 20 Kelvin is warmed before it goes into the fuel cell. This is done by the fuel cell heaters, with their switches located here. The on position automatically maintains the correct temperature. Off would shut off power to the heaters and would not normally be used once the fuel cells were operating. If the temperature of the coolant dropped too low because the fuel cell is not producing enough power, this indicator here reading fuel cell radiator temperature low would become striped, and the fuel cell radiator switch here could be set from normal to emergency bypass. So part of the radiators would be manually bypassed and the temperature would go back up. There is an indicator to tell you what position the valve is in, striped for open and gray for closed. Normally this emergency bypass would stay closed. Impurities would build up in the fuel cells from time to time and they would need to be purged on a regular basis. This was done using the fuel cell purge switches seen here and the H2 purge setting seen here. The hydrogen purge valve is opened, allowing a high flow of just hydrogen to go through the fuel cell, flushing out impurities. This was then vented overboard. The O2 purge system opens the oxygen purge valve and the same process takes place. Then both purge valves are closed. The hydrogen purge line heater switch seen here had to be set to on for at least 20 minutes prior to hydrogen purge to avoid freezing the water in the system. The fuel cell's performance could be monitored here at fuel cell instruments, which showed oxygen flow, hydrogen flow, skin temperature, and condenser outlet temperature when this switch is set to fuel cell indicator. These should all be reading green. If the pH of the exhaust water gets too high, this switch labeled pH talkback would show a striped pattern. This would indicate an electrolyte leak of the potassium hydroxide into the water. That fuel cell would have to be shut down, as this would make the water too toxic to drink. Fuel cell 1, 2, and 3 lights will come on and a master alarm will sound if there is a critical fault in any of the fuel cell monitoring systems. All of this had to be done with precision and timeliness to ensure the proper operation of the Apollo alkaline hydrogen oxygen fuel cells. Now let's look at the battery systems. Here you see 3 silver oxide zinc batteries that produce 29 volts with 40 amp hours, giving 1,160 watt hours. These are designated A, B, and C and are seen here. Batteries A and B are used in normal flight operations and can supplement fuel cell power if needed. Battery C was usually reserved for use after service module separation. All 3 batteries were recharged from the charging system here. There are also 2 23 volt 0.75 amp hour silver oxide zinc batteries for pyrotechnics labeled Pyro Battery A and B. We'll get to these. Command module power from the fuel cells was sent to these buses for distribution to all the systems you see here. We will not get into these. Suffice it to say, they powered everything. The pyrotechnic batteries are isolated from the rest of the system because you don't want some other system shorting out and causing a power surge through your pyrotechnic system. The pyrotechnic system is used to fire explosive bolts for separation and to fire blades called guillotines to sever wire connections when necessary. Now let's take a quick look at the diagram for the lunar module, which used the same type of silver oxide zinc batteries that the command module used for backup power. These batteries again generated 28 volts DC and 400 Hz AC. Pay close attention to this section because all 3 of the modern spaceflight capsules, the SpaceX Dragon, the Lockheed Orion, and the Boeing Starliner, use battery systems with solar power instead of fuel cells. The Dragon capsule has flown, and it is the first American space system with humans on board to fly without fuel cells in about 70 years. That doesn't mean fuel cells won't be important for space colonization. They absolutely will be. But you need to understand battery power systems also. Now here's the diagram for the lunar module. First, we have the batteries themselves. There were 5 descent stage batteries with 400 amp hours each, and 2 ascent stage with 296 amp hours each. There was a glycol cooling loop to prevent overheating. Here we see the electrical control assembly subsystem. Power from the batteries was sent here next. There are 2 for the descent stage and 2 for the ascent stage. They could provide high or low voltage to the buses, which would distribute the power. And the ECAs had a primary and backup path. These ECAs had switches to turn on or off individual batteries and circuit breakers to protect them from over or reverse current. These batteries were stored here for the descent stage and here for the ascent stage. Remember, the descent stage stays on the moon. The ascent stage took the astronauts back up to rendezvous with the command module. Next, we have the interface control system. We use the Launch Control Center power input to keep the batteries charged until the last minute. Then we disconnect prior to launch. LUT stands for Launch Umbilical Tower. RJB stands for Relay Junction Box and was on the Lunar Module pilot side. It contained controls and automatic check equipment for the command module and lunar module systems. While DFRB stands for Dead Face Relay Box and was on the commander side. The dead face is a circuit that allows the battery system to be disconnected prior to connecting or disconnecting the circuit. It's like turning a device off before unplugging it so you don't get an arc. This system allowed the descent stage to be isolated from the ascent stage prior to liftoff from the moon, with the switch seen here. This part is called the DC feeder subsystem. It provides direct current to the bus so it can be distributed to the systems that need it. Direct current is a continuous one-way flow of electrons. It is what computers and most other equipment need. You see DC power being distributed to the lunar module subsystems here. Things like electric motors for fans and some other equipment work best with AC power. AC is alternating current, where electrons are pushed through a wire, then pulled back temporarily, then pushed through again. This causes a current to reverse itself, and the speed of these reversals is measured in hertz or cycles per second. Most household power is 60 cycles per second in the United States, but the Apollo systems were 400 hertz. Appliances that need DC power usually convert it from alternating current to direct current using something called a full bridge rectifier. To go from DC to AC, we use an inverter. You can see them here also. The AC subsystem takes the alternating power from the inverters and distributes it to the components on the lunar module that work best with AC current. You also see an external feed here to provide power from the outside or ground service equipment. So outside power sources would be used prior to launch. After that, everything had to run on fuel cell and battery power. Every complicated looking diagram is understandable if you know the code and break it down. I suggest drawing out several times any schematic you want to remember well. Now let's quickly go through this system one more time. The batteries are here, and their power is sent by direct current to the electrical control assembly for monitoring, manual switching, and circuit breaker protection. We see one set for the ascent module and one for the descent module. The power then goes to the interface control system. It allows power to be distributed to different sides of the ship and allows power to be cut prior to a disconnect to prevent arcing. This is called a dead face. Next, we have the DC feeder subsystem, which takes the DC power in parallel from the ECA systems and sends it to the bus, which is where you connect your devices to the power system. The buses send some DC power on to inverters, which turn it into AC power. The AC power subsystem then distributes AC power to the systems that work best with alternating current. Now you can look at these diagrams and understand the different subsystems and their purpose for both the Apollo command module and the Lunar Excursion Module. Though the components are usually smaller and more advanced, current power distribution systems will look remarkably similar. If SpaceX, Boeing, or Lockheed Martin ever release the schematics for their capsules, we will go over them in depth. Now we have a good understanding of the fuel cell and battery technology and power systems design of the Apollo missions. The Apollo capsules are still today the only manned spacecraft to leave low Earth orbit. Thanks for listening and stay safe.